All right, hello everyone. We'll go ahead and get started now. My name is Skyler Teel, and I am a stress engineer for SDA. And today we'll be talking about element quality and how that applies to the finite element method. And then we'll go over some tools in Femap that help you to maintain and evaluate your element quality. So just as a brief outline, like I said, we're going to talk, we're going into a little bit of the motivation behind why element quality is important. And then we'll discuss a specific element quality known as the Jacobian and sort of, how that relates mathematically to the finite element process. And then we'll do a demonstration in Femap. So, like I said, element quality, it's very important when it comes to the finite element method. Ensuring satisfactory element quality is of specific interest, especially when it comes to the quality known as the Jacobian. And that essentially describes how a meshing element is manipulated. And if you can see in the figure, in the left, in green, there are some very square elements that would have a very well-defined Jacobian, which is sort of what we were going for in a finite element analysis. And on the right, you can see elements in red that don't have a very good Jacobian. And a quick note here, the scale that Femap uses for the Jacobian is actually the reciprocal of the value that I will define later on, and that's just important to note. So just to give a bit of context of where we are in the big picture, the finite element method generally incorporates 3 steps, and we'll relate our discussion on element quality today to the second step, which involves mathematical computations over the domain of the finite elements. To begin with, the essential idea with finite element analysis is to simplify the computations by evaluating expressions that approximate the values of interest to the problem. And essentially what you do is you transform the problem and then evaluate the expressions using what are known as interpolation functions. And essentially what happens is you have general quadrilateral elements that are transformed or mapped to a square master element, at which point mathematical techniques such as Gauss quadrature are used to numerically integrate the interpolation functions under specific conditions. And in the figure you can see a meshing element in blue and how that is then transformed into a master element on the right. The transformation of a meshing element to a master element is dictated by what is known as the element Jacobian, as I mentioned before. And geometrically, the Jacobian describes how an element in the global meshing coordinates is mapped to a local coordinate system of a master element. And you can kind of see this mathematically by equation 7. This transformation is satisfactory if and only if all the points in the mesh element are mapped uniquely to points within the master element. This is known as a one-to-one mapping. Very briefly, mathematically, the Jacobian is a matrix of derivatives describing the rate of change of these global coordinates with respect to the local coordinates of your master element. And here's a brief sort of illustration, visual illustration, depicting an element that would have a very unsatisfactory Jacobian. And you can see on the left there's an element that has an internal angle of greater than pi. And you can see in the figure that these elements are generally avoided in any finite element analysis. And essentially when you have an element with an internal angle of greater than pi, a non-satisfactory Jacobian, or rather, this element will not produce a satisfactory Jacobian everywhere in the master element on the right. And the shaded area of the real meshing element on the left does not exist as part of the actual element, yet is mapped into the bottom right-hand corner of the master element on the right. this mapping is not one-to-one. This area, you're getting information mapped to your master element that doesn't actually exist in your mesh as you've created it. So now that I have a just very brief background on the elements of it, or the element quality of interest, we will go into Femap and sort of do some basic demonstrations as to how you can manage and identify your element quality. So essentially what we have here is I made a very simple model of an I-beam, and as you can see, the elements in this particular model are very square, very neat mesh. And what I did was I fixed the model in one end, so it's essentially a cantilevered beam, and I applied a tip force on the other end, and I deflected it. So you can see here with the very square elements, a very nice contour. There's no discontinuities within the stress contour. It's what you would expect to see in a well-posed finite element problem. To compare this, I essentially made the same model, but with some very poor elements at the beginning. And this brings me to the first feature of Femap that I'd like to highlight. We can identify these elements as poor elements regarding the element quality that we want to check by using the meshing toolbox. And one of the tools that I use pretty often is this surface mesh quality tool, where essentially you have this drop-down box of different element qualities that you can inspect by giving Femap a max allowable value. For instance, if we want to check the Jacobian of the elements present in our model, we can give a max value of, in this case, 0.6, and it will show us which elements are failing. And back to the original analysis that I did with the cantilevered beam with the tip force, we can see that with the poor elements that failed our Jacobian check, there are very obvious discontinuities within our stress contours. And it can be seen that the contours of the elements with poor element qualities are discontinuous, and it appears to be spurious stress peakings as well. So if you do have a mesh that features elements that don't necessarily meet the standard of element quality that you wish to have, there are a few tools that you can use to then fix your elements. The first of which is also in the meshing toolbox, and it is the mesh locate tool. Essentially what this allows you to do is, in real time, based on an element quality that you give it, you can manually drag nodes and fix the elements to a point where they satisfy the element quality check. For instance, so if we want to fix these elements, which again, based off the surface mesh quality tool with a max allowable value of 0.6 for the Jacobian, we can use this dynamic feature to manually move the nodes And we can see in real time as the Jacobian satisfies the allowable value that we've given Femap. So this is a pretty useful tool just to sort of spot check elements. Like I said, I use it pretty often. And it's pretty easy to use. And when you're done moving the nodes around, you just hit save and it's fixed your elements. Another method that you can use to sort of help to create elements that are more acceptable is using the size along curve or size on surface tool, which I will demonstrate now. So first, we will delete the mesh that we have. So the mesh size along curve tool actually allows you to define how many mesh seeds you want to have along a curve. For instance, I can give it a number of elements, or if you have a certain element size in mind, you can also put that in here. For instance, if I wanted 1/2-inch elements, you can do this as well. And essentially that says it's going to put 20 nodes along this line, or this curve rather, that I have highlighted. In a similar manner, you can use a size on surface tool, which essentially does the same thing, but it allows you to size an entire surface at once. Again, so if I have a certain element size in mind, for instance 0.5, I can size that surface. So with that surface size, we can go and actually mesh the surface. And an important thing to point out here is this max quad box. For geometries that are irregularly defined and not as neat as this square cross section of the shear web that we have here, this is helpful in that it'll put as many quadrilateral elements into the domain as possible. Also, with this mapped meshing option right here, you can turn it on or off. With the mapped, it sort of helps it create a clean mesh to the best of Femap's ability, given the domain that you're meshing. And as we can see here, it's created a very nice, organized mesh for us. So now that we've fixed our elements in the shear web, we can actually go ahead and rerun the brief analysis that I did previously. We can see how that compares. So as you can see, the stress contours are very much more continuous now. And it doesn't seem like we're getting any false peaking anymore in the region in the shear web that we fixed. And as a final tool that I can introduce to check the element quality throughout your entire model, you can use Tools, Check Element Quality, which allows you to select a various range of elements, for instance, our beam. at which point this box opens up where you can check various element quality aspects with different allowable values. For instance, if we wanted to check aspect ratio, skew, as well as Jacobian, you can initialize those and hit OK. And it will actually tell you how many elements in your selection have failed the given criteria. So it's pretty helpful when you're trying to determine if your mesh is acceptable from a global standpoint. So, in conclusion, like I said, the element quality criteria, specifically the Jacobian, needs to be satisfied in order to have confidence in the results of a finite element analysis. And just to review some of the tools that we went over to help maintain and manipulate the element quality, we have the meshing toolbox, which features the surface mesh quality, as well as the mesh locate and mesh sizing tools. And also from the drop-down toolbox with mesh, you have the size along curve and size on surface tools. And finally, I introduced the tools check element quality feature of Femap.
So Skyler, you had two questions come in.
Okay.
The first one was, how can we determine the maximum allowable Jacobian value for a given element type? For instance, 2D surface elements.
2D surface elements.
So the default is 0.6. What's the maximum you can allow?
I'm not 100% sure off the top of my head because, like I said, Femap inverts that number, I think, just so it can be compatible with some of the other element quality numbers that it gives, just so you can actually do a combined quality analysis. So I may have to get back to you on that one.
And then, so yeah, my understanding is in the Femap world, less than 0.6. That's their recommendation for the best results.
Okay.
And then is the Jacobian only appropriate for 2D elements, or what about 3D?
I'm not sure how a 3D element is actually mapped to a master element in finite element analysis in terms of a mathematical process. What I presented is more related to 2D elements. It may very well may be a different process for 3D elements.
Yeah, let's take an action to get an answer for 3D, because there's even another one that came in about 3D.
Okay. Sure. I will make a note of that.
So somebody wants a copy of the charts, and yes, everybody can have a copy of the charts, and we'll post the recording. We do that every time we do one of these. And then the last question is, what's our typical values for elements passed for various element types for MSC Nastran? I think Nastran calculates it different, and we could summarize that as well in a follow-up.
Yeah, I think that goes back to what I was saying about Femap inverting, or it's the reciprocal of the number. It's numerically the same value, just Femap displays it differently. I think that it displays the reciprocal.
Right. Another question, what number of bad elements is allowed? I think I can answer that one. You really don't want any bad elements, but there will be times where you cannot avoid them, where you just cannot get it to pass.
And you'll have situations where, for instance, if you have a cutout in a bulkhead region, you want to make sure that your element quality around that cutout, especially if you're analyzing the cutout itself, you want to make sure the element quality is good around those features. Far removed from those features, you might be able to get away with having less than satisfactory element quality if it's a must that you have to have it.
Right.
From a geometrical standpoint.
Question on, can you use mid-side node element to reduce the number of bad elements?
So
That's a different mapping, right? When you have a
yeah, the mid-side element actually uses interpolation functions that are of higher order. The interpolation functions that I presented are very basic linear interpolation functions. And essentially the more nodes, the higher order your elements, you know, complex your interpolation functions get. And the mappings at that point become different. But it's the same general idea. You're taking this quadrilateral element and you're moving it to you know, a nice square master element that facilitates the numerical integration of the computations that are being completed.
Right. Let's see, another 3D question. Does the dynamic tool to fix bad elements work for TED elements?
I'm sorry, can you repeat that?
Does the dynamic tool to fix bad elements work for 3D TED elements?
You know, I've actually never used that for solid elements before. I imagine
there's a lot of interest in this. I would say let's do something similar for 3D solids and elements. Okay. We'll take that as an action to answer these questions, but then it's a good idea for another webinar in the future.
Okay.
Awesome. If you guys have any more questions, feel free to email. Put your picture back up, Skyler. You can email Skyler. He's done a lot of research into this. Or email Chris or Marty. We'll get you an answer. We'll make the slides available, and we'll make the recording available to anybody who wants it. And we'll talk to you all later.
All right. Thank you, guys.